So it's our very great pleasure to have today with us Professor Jeff Hangst from Aarhus University and from the Alpha experiment. Professor Hangst, he graduated from MIT and from the University of Chicago. And since '94, he's been in Aarhus University, but since 2001, he's been stationed in CERN, where he was the co-founder of the Athena project and later of the founder and the spokesperson for the Alpha experiment, which we'll hear all about. It had many amazing achievements, including the production of antihydrogen and the spectroscopy of antihydrogen. And when we invited him to give this talk, he told us it's a great timing because in the beginning of the month, they'll have new results published in Nature, which is an amazing achievement, which we'll hear about now. Professor Hangst has many awards, including a member of the American Physical Society and the Royal Danish Academy of Science. And thank you very much for being here today.
Well, thank you very much for inviting me. This is a real pleasure. As I explained before, I'd much rather come to your lovely country to give this talk, but we'll have to arrange that later. Okay, so Alpha, we work at CERN, but we're a small experiment by CERN standards, about 50 people. These are the institutes. You'll notice we have one Israeli collaborator, that's Eli Sarid from Negev. And he's been with us from the beginning, an expert in plasma physics, which is one of the key ingredients to making any of this work. What's wrong there? Okay, so the acronym stands for Anti-Hydrogen Laser Physics Apparatus. This is from 2005, and I can promise you we had no idea how to make a laser physics apparatus at that time. This was an incredibly ambitious name for the experiment. Turned out okay. About 24 faculty, 13 postdocs, 10 PhDs. And during the summer, we have up to 20 undergraduates, at least we did before COVID. We're a very popular experiment with the undergraduates who come to CERN for the summer program. Just before we get started, I want to point something out to you that a lot of people have a very negative reaction to antimatter because it sounds evil. They think of the Antichrist or something, and maybe we should change the name. You see here a real YouTube video. CERN creates hell on earth by collecting antimatter in recent experiments from conspiracy theorists. Now these people, they make better videos than CERN does. I don't know where they get the money for this, but I was totally convinced that I was some sort of evil genius after I saw one of these. So I'm suggesting we change the name. How about alternative matter? We have alternative facts, so why not alternative matter? And in fact, isn't that what we're talking about? That's what we think antimatter is. It is an alternative to building the universe, and we kind of don't understand why that didn't happen, right? A little more seriously, the physics question that we're trying to answer, I've got Mr. Dirac and Mr. Bohr here. The standard model now predicts that hydrogen and antihydrogen should have the same spectrum. They should obey the same laws of physics, if you will. So a very fundamental question, do these two systems behave in the same way? And hydrogen is one of the things we understand the best in physics, maybe the thing we understand the best by far in all levels of classical and quantum theory. So here's a really golden opportunity to put nature to the test by doing precision measurements on an anti-atom, if you could make one. Of course, for me, I work in Denmark. So how could you work in Denmark and not want to know the answer to this? Because obviously Niels Bohr is a Danish hero. And so I'm hoping I could get my face on a bill or something if I can do some good anti-hydrogen physics. If we look a little more deeply, what we're doing is tests of fundamental symmetries using precision atomic physics techniques applied to anti-atoms. Now, when you talk about precision, you want to get an atomic physicist, right? Those are the guys who know how to measure. These high energy guys, they measure something to 1% and they call a press conference. If you're doing atomic physics, you're dealing with precision physics. CPT violation, if those two spectra aren't the same, you have direct evidence for CPT violation. This is the last symmetry that's left, right? And everything else has been violated singly or pairwise. If you look at people who speculate about physics beyond the standard model, CPT violation and Lorentz invariance violation normally appear together. It's kind of inescapable. So we're looking primarily and fundamentally for physics beyond the standard model. Could there be some slight difference between these systems that we haven't seen yet? The second big perspective that's coming very soon is anti-gravity. We don't think there's anti-gravity, but gravity on antimatter. We have no direct measurements of how antimatter behaves in the gravitational field of the Earth. There were 2 previously approved experiments at CERN. We've made a proof of principle experiment in the older Alpha device that shows how to do this in a machine like ours. And we've built a new machine called Alpha G, which is ready to go when we start up again. This is all motivated by the apparent baryon asymmetry in the universe. We simply don't know why the antimatter seems to have disappeared, leaving the matter behind. Now, none of the things that we do are directed exactly at this question, but the philosophy is sort of, if you can get your hands on some antimatter, you should look pretty carefully to see that there's not something we haven't overlooked. And atomic physics is a very good way to look carefully. So our initial physics goal back when we started in 2005 was to trap antihydrogen. We had already produced it in low energies. The idea is to then keep it around so we can study it in detail. And for me, the thing that motivated my participation in this at early days was to this very beautiful transition in hydrogen, the 1s to the 2s. This n equal 2s state is very long-lived. That means that the spectral transition is very narrow. It's a dipole forbidden transition, so you require 2 photons. It's Doppler-free if you use counterpropagating photons. And this is measured very accurately in hydrogen. This thing on the right we call the Hench plot shows the precision of that measurement as a function of time. Today, this transition is measured to a few parts in 10 to the 15. And it's not just a precise experiment, it's an accurate experiment because the frequency reference is an atomic fountain clock, which is the same type of thing that's used to define the second. So this is what we mean when we talk about precision measurements. High precision spectroscopy referenced directly to the SI second. That's the whole idea here. Of course, if you can trap antihydrogen, any type of spectroscopy could be implemented, and I'll show you some alternatives to this. But this was the one when CERN was first getting into this business. CERN's a high energy lab. They're not so interested in atomic physics, but they are interested in symmetries and symmetry violation. So this particular transition was always looked at as the most promising candidate on looking very carefully. The machine we use at CERN is called the antiproton decelerator. We don't have a lot of time to go into this, but quite simply, protons are run into a target. A lot of junk comes out the back. Some of that junk is antiprotons. They're collected and momentum selected and injected into a storage ring. Now this storage ring was left over, or parts of it were left over from the seminal experiments in the 80s where CERN found the W and the Z particle, right? So by doing proton-antiproton collisions in the SPS at that time. So a lot of the techniques that we need to deal with the secondary beam of antiprotons were developed at that time. Just to put some numbers on this, they're injected at a few GeV and slowed down to 5 MeV in a cycle that lasts about 100 seconds nominally. Now, if you slow down the accelerator, a beam in a storage ring, it will eventually just grow and hit the wall. You can convince yourself of that on the back of an envelope. Deceleration is much more difficult technically than acceleration because the opposite happens when you accelerate a beam. It actually gets smaller transversely. The techniques to counteract that were developed by Vandermeer again, in connection with the WNZ project back in the 80s. He won the Nobel Prize for the stochastic cooling technique that was used at that time. Again, I could give a whole colloquium on just how this machine works. I always tell guests, this is the coolest and most complicated conceptually machine at CERN. Okay, just some numbers. We get about 30 million today antiprotons in a 200 nanosecond bunch every 100 seconds or so. And then up until recently, the normal way this operates is one experiment gets 8 hours a day, and we rotate the shifts in 24 hours. Now, what do you do with 5 MeV protons? You've got to stop them. And the way that we stop them is quite simple. We run them through an aluminum foil. We call that the degrader. So you get a bunch of antiprotons that are coming into a penning trap. This is a penning trap with a large axial magnetic field. And then these yellow things are cylindrically hollow electrodes where you can put a voltage. So what you do, the antiprotons come in, slow down in the degrader. A lot of them slow down, stop, and are lost. Some of them don't slow down enough and are lost. But if you have some that are less than, say, 5 kilovolts, and you put 5 kilovolts on the end electrode, they'll be reflected. And before they're reflected out of the trap again, you slam the door on them by switching another high voltage electrode in about 10 nanoseconds. And then you have antiprotons bouncing around in this penning trap. They're confined transversely by the solenoid field, so they're spinning in the plane perpendicular to the screen and bouncing back and forth. Now, another trick that's been done here, put some electrons in the same trap. Electrons have a negative charge, so they can be in the same potential well as antiprotons, but they also have much smaller mass, so their cyclotron motion in the 3 Tesla field causes them to radiate their energy away. Remember, that was the problem with the Bohr atom before Bohr. Why did atoms survive? Why don't the electrons in atoms simply radiate their energy away and collapse into the nucleus? Well, here that actually happens. You put them in a magnetic field. This whole device is cooled to 4 degrees Kelvin by liquid helium. So the electrons just fall to the bottom of this well. So now I have cold electrons, and I have this energetic antiproton cloud up to 5 kilovolts, and it's bouncing around and in real space bouncing through the electron cloud. So it just collides slowly and falls to the bottom. So this is electron cooling of antiprotons. It happens for free. You just wait sort of 10, 20, 30 seconds, depending on your field, and the antiprotons will fall down. These techniques were developed by the TRAP collaboration at Lear, which is the predecessor to the AD back in the late 80s and 90s. And we still use the same thing today. Very nice electron cooling at rest. Here's a picture of the Athena catching trap. You see the high voltage electrode, the electrodes for forming the well, and over here is the electrode that switches quickly. In the AD now, we get about 100,000 antiprotons captured every 2 minutes from a single AD shot, right? That's a factor of 10 better than we did in Athena. That's of the 30 million that arrive, okay? So it's a poor man's slowing device, this aluminum foil, but you can buy it in the supermarket. Now, to make antihydrogen, you also need positrons. The technique there, again, I could give a whole colloquium on this, but in brief, this whole thing was developed by a guy called Cliff Serco in the University of California, San Diego. We get positrons from a radioactive source. It's artificially produced. It's just sitting there emitting positrons. They're magnetically guided into another penning trap. The difference this time is instead of doing timing, because we don't have timing like we did with the antiproton bunch, the positrons are just slowed down using differential gas pressure. So there's some nitrogen gas inside here, high pressure on this end, a lower pressure on this end. The positrons just slow down by collisions with the nitrogen gas and fall into a penning trap well at the left side. Okay, again, we don't have time to go into that. Brilliant device. You can actually buy these now. Every experiment that's doing anything like this has something like that. Okay, how do you get them together? Well, because they have opposite signs of charge, You can't put them in the same potential well, antiprotons and positrons. The solution here is the so-called nested potential well, you see at the bottom here. So this central well is upward curving and can confine positrons. Then the large well formed by the other two lobes curves downwards and can trap antiprotons. Okay, that's the voltage space. In real space, it looks like this. Putting positrons in a big magnetic field, they also radiate their energy away and make a nice cold cloud of positrons. Then you just dump some antiprotons in and let the positrons cool the antiprotons so that this reaction happens. Now, one of the big issues getting into this back in the sort of 90s was how would you show that you've made antihydrogen? Now, the Athena innovation was to use a detector that could detect both the antiproton and the positron annihilation. Because here we have charged particles that are captured in these nice penning traps, but as soon as you make a neutral antihydrogen, it just walks off to the wall and annihilates. Now, so we're going to mix the techniques of high energy physics for particle detection with our low energy plasma physics here, and then you can detect antihydrogen. So we had a silicon detector in the center, cesium iodide crystals to detect the gamma rays from the positron annihilation. I'll show you what an event looks like. By the way, when we're all hanging out in CERN back in the beginning of these experiments in the AD, this was the time that Dan Brown came and visited and got inspired to make the angels and demons thing and destroy the Vatican. This is the Athena detector. You see, these are silicon strips and pads, 2 layers of silicon. Those detect the charged pions that are produced from an antiproton annihilating on a nucleus in the wall of the machine. The gamma rays from the positron, this is positron annihilating essentially at rest. So the gammas are back-to-back 511 keV. All right, there you see a picture of the detector with the little sugar cube size. So, I mean, to us, it was just obvious that, you know, antimatter, it's horrible to work with. The only good thing about it is that when you lose it, you should know it. And that was the philosophy here. We're going to use what we know how to detect to show that we make antihydrogen. So when we did this the first time in 2002, there was a whole lot of competition with our rivals. And we sent this to Nature, and we thought it should be on the cover of Nature. So I stayed up all night coloring in this event diagram, which was really just the blue that you see, to make it sexy enough to get on the cover of Nature. But that didn't actually work out. They had a special issue on malaria that week, and everybody agreed that was more important than antihydrogen. But somebody just stole my picture and put it on the cover of a textbook in the States that cost $200, and I made zero money from that. Okay, the signal for antihydrogen is quite simple. You see the pions making a vertex from the antiproton annihilation. The 4 yellow lines in that picture are pions. By the way, it's not always 4, it can be 2, 3, 4, 5. There's a distribution, obviously. So you find that vertex, and then you go looking for gammas in your crystals and say, do I have 2 511 keV gammas? And if so, what's the angle between them, between the vertex and the crystal? That angle should be pi. So this is a number of events versus cosine of that angle, and pi has a cosine of -1. So this peak on the left here was the first ever signal for low energy synthesis of antihydrogen. And interesting thing about this, it's not like the Higgs boson. You can turn off the interaction by heating up the positron cloud so that the combination is suppressed. And when you do that, you see the peak goes away. This is a very clean, nice experiment. In the first experiment, we had 131 of these events. If you put in the efficiencies, that first ever experiment made 50,000 cold antihydrogen atoms in the course of a month or so at that time. Okay. So that was a big deal for us. And by the end of the time in Athena, we were making antihydrogen at about 400 to 500 per second when we did a mixture of. The detector could have seen 1 per day. So this was a counteraction of Murphy's Law, we had a lot more antihydrogen than we ever thought we would ever have. And so we decided to press on very quickly. I decided to press on very quickly and get into trapping. Now, how do you trap neutral atoms? The typical way for matter is the so-called Yoffie-Pritchard geometry, where you have a quadrupole, a magnetic quadrupole, and two sort of solenoidal coil, they call mirror coils. And what this makes is a configuration with a minimum B in the center here, okay? So the interaction, the potential energy is minus mu dot B. These are highly polarized at these fields, so it's really mu times B. So you can make a magnetic minimum trap for using the dipole moment of a neutral atom, okay? The bad news is that these are really shallow, weak traps, okay? So the number to keep in mind for hydrogen, the well depth that you could get, and we're using temperature equivalent, 0.7 degrees Kelvin per Tesla of delta B. So the difference between the B in the center of this and the edges times 0.7 Kelvin. The alpha trap has a depth of about 0.5 Kelvin. That's using state-of-the-art magnet technology. It's really difficult to do any better than that. But the thing you'll see here is that the whole concept and what we pioneered in alpha, you produce the atoms so that when they're born, they're trapped, right? So that they're actually made at the center of the trap and can't escape, okay? Now let's look at a little video of how all that works. It's really much easier to look at it. And after this, I'll take some questions if people want to. So this is the central part of the alpha concept. This all sits inside of a big solenoid magnet to provide the field for the penning trap. What you're looking at now is the silicon detector, 3 layers of double-sided silicon for looking for the antiproton annihilations. And now you're looking at superconducting magnets that make up the atom trap to actually confine the antihydrogen atom. So we're gonna have to make them inside there and make them cold enough so that they don't escape. We use an octopole for a lot of technical reasons that I don't have time to get into today, rather than a quadrupole. That's a key feature, by the way. It's absolutely essential to what we do, but we don't have time to talk about it. That's all in a liquid helium bath. These magnets are energized and ramped up and down. They're not persistent, so they're connected to the outside world all the time. Now, inside the vacuum chamber are the electrodes for the penning trap. And the idea here is you get yourself a positron cloud from your positron accumulator. You put it in this center of this nested well. Then you get your antiprotons from the AD that you've cooled and calmed. And you slowly merge them together. And slowly is the key here, because I'll show you in a minute, the energy levels are really a problem. What we think happens is 2 positrons collide in the field of the antiproton. One carries off the binding energy and you have antihydrogen, okay? By the way, it's typically formed in a Rydberg state, a highly excited state, and has to decay while maintaining its kinetic energy and polarization. But there you get an idea of what the magnetic potential looks like. If your antihydrogen was formed cold enough, it'll just be stuck there. How do you know you have it? Well, originally we intentionally release it. So we mix some antiprotons and positrons, wait a little bit, and then release it to see that we actually get a signal from the antiproton annihilation, okay? By the way, we're not looking for the positrons anymore because there's too much absorbing material in the magnet construction to have any efficiency for that. Now I'm going to show you how you do a typical experiment with trapped antihydrogen. Here I'm showing 2 atoms trapped, and now I'm going to shine the laser on them to do the 1s, 2s excitation, all right? This is actually a retroreflected laser that makes a cavity inside the cryogenic vacuum system. Those are the 2 photons that just excited the 1s to the 2s. A third photon from that same laser will ionize the atom. So now that it's not trapped anymore, because most of the magnetic moment comes from the positron. Once it's gone, the atom just comes out. So a very important point here for everything else we're going to talk about. everything we do depends on killing the antihydrogen. In other words, using resonant radiation to somehow knock it out of the trap so that we can detect it, right? We have no chance of, we don't have 10 to the 15 atoms that we could do fluorescence spectroscopy. Everything depends on the high sensitivity detection of the annihilation, right? So are there any questions at this point?
Yes, I'd like to ask something, if I may. Okay, so most of what happens in the atom is actually electromagnetic, right? It's not. Now, I'm sure we know very well the very good limits of the charge difference between electrons and positons, protons and antiprotons, and so on. So you don't expect any electromagnetic effects, right? Which is the bulk of the, let's say. So where do you expect difference to come from, if at all? I mean, from there's no strong, I mean, the electrons are only weakly and electromagnetically interacting. So where exactly do we expect differences to come from?
Well, we're not expecting, I mean, as an experimentalist, I'm also not allowed to expect a difference, right? I have to build my experiment so that it's completely.
Yes, but to be blunt, you don't want to waste your time, right? I mean, I can suggest many experiments that you would not do because, even if the questions are in principle very acute. But so I mean not.
Okay, you're making assumptions that the electromagnetic interaction is all that goes on here, and also that you'd be surprised we don't know the charge symmetry between positrons and electrons and antiprotons and protons very well.
If electrons and positons decay into photons that have no charge, and of course, if we assume charge conservation, then
you have.
I think we do have a good limit.
This is an example of what you really know from experiment and what you can assume that you know. And all of these things are currently being measured to high precision. That's another part of the CERN program. Both the charge, I'll show you an experiment in a minute to measure the neutrality of antihydrogen. You can say that you know that, but until it's been measured, you don't know that. And that's the whole point here.
I understand, but that is true of so many things. But the question is, do you spend 15, 20, 30 years to check these things?
Well,
I'm sorry, I'm not questioning the importance of the experiment, but surely there must be some rationale behind doing the experiment.
If you're saying, is there a model that predicts,
for example,
difference?
What will you be testing? What will you be testing? I mean, usually, okay, so let's say you find nothing at the level of 10 to the minus something, but what exactly will you learn about something from this number? That's what I'm asking.
You'll learn that CPT is still a good symmetry in this system. That's the strong statement that you can make about this. And no matter what you tell me about high energy physics experiments in CPT, there's nothing that compares to this type of a direct comparison between hydrogen and antihydrogen. Maybe we can continue this later, or we're not going to go into it. It's a very good question, but let's move on and see the results. So why is this difficult? 1 electron volt of kinetic energy corresponds to about 12,000 degrees Kelvin. That's just a Boltzmann constant. The antiprotons were initially captured at 5 kilovolts. That's 60 million Kelvin. Even if we get it all cooled down to where it's barely moving, the cloud of charge like this has space charge energy of a few electron volts. So if you had 0 temperature positrons and antiprotons of the numbers that we're using here, just moving across the cloud would change the energy by electron volts. And remember, the trap for neutral antihydrogen is 0.5 Kelvin deep, okay? So that's what's hard about this to get trapped antihydrogen and why alpha is the only experiment that's ever succeeded in doing this, this mismatch in energy. It's really very, very difficult to start with charged particles in traps that we can manipulate and make something that's sort of tens of micro electron volts that you can trap. A lot of technology in this that we've developed over the years. There's a picture of the octopole magnet being wound. There's only one place that can make this magnet, that's Brookhaven National Lab. Again, we could spend a whole day talking about this. When we were starting to look at antihydrogen, you think you have some trapped, you don't want to hold on to it for a day and release it slowly. You want to get out, knock it out quickly to minimize the background that might show up while you're releasing it. So we developed a system for very rapidly shutting off these superconducting magnets in milliseconds, tens of milliseconds. The B&L guys who made the magnets sort of laughed at us and said, okay, that's a nice trick. You'll do that once and then you can come back and we'll build you some new magnets. But it turns out that they were quite robust and this worked for a long time. So in the early days, the experiment to try to find antihydrogen trapped was to mix the particles, knock out any remaining charged particles, and then release the trap to see if you got an antihydrogen annihilation. There's the silicon vertex detector for alpha. You're looking at about 1 million pounds of silicon. It doesn't know it's in a low rent experiment. It thinks it's in Atlas or CMS, and so it's really expensive. Compared to a high energy physics experiment, there's not much going on here. The antiproton annihilates into pions. We can see their curvature in the 3 layers of silicon and reconstruct the vertex. The other thing going on is cosmic rays. So a muon can come screaming through, and if it intersects the sort of circumference of the Penning trap, then it could look like a 2-prong antiproton. But the good news is that we can measure both of these independently of the experiment. We can put some antiprotons in, knock them out, and see how they look. And we can take cosmic data for months and then tell the machine to learn how to distinguish the two. So we're using the same type of machine learning techniques to suppress the background. The first trapping result was 2010. And the only worry we had at that time was, how do we know that what comes out was actually neutral? Because there is a chance in this magnetic field configuration that there could be some antiprotons left over, even though you pulse electric fields to try to get rid of them. So the solution to that was to put on a bias field along the trap axis as we were releasing them. And what you're seeing here are both data and simulation of the first time that we actually succeeded in doing this. So what do we have? If it's an antihydrogen atom, it's a magnetic dipole trapped in a field which we've designed. So we can do Newtonian dynamics in that situation and calculate the trajectories and see how they would come out, right? So the simulation is the gray dots here. What's plotted is the time after we start turning off the magnets, 0 to 30 milliseconds, versus the axial position where the antiproton would annihilate. Okay, so the center of the trap here. And the gray dots are the simulation of what you would see if you had neutral particles. The color codes, blue, red, and green, are for when we put on the left bias field, the right bias field, and no bias. The bottom plot, these little scatter plots, show what would happen with those fields if what you were trapping were real antiprotons, not neutral antihydrogen. And the rest of it are the data, right? So we had some number of these runs at this time. We got these indications of antiproton annihilations, and as you can see, the distribution agrees very well with the neutral one and not at all with the antiproton hypothesis. So that was 2010. By the way, there were 38 events in that. On the average at that time, we got an event 1 every 8 times that we measured, that we did this experiment. So keep that number in mind. That was the first time. This was voted Physics Breakthrough of the Year in Physics World magazine. I always tell people this matters not at all, these kind of things, until they happen to you. And it was one of the top 10 stories of 2010 in the AIP, and it was the most clicked on story on the Nature website for all of 2010. You can tweak it once you have a signal. This was by the end of that same run, 2010, we had a lot more events. We started to get them with greater frequency, and things just kept improving. The next experiment was to measure how long you could hold the antihydrogen. The early answer was at least 1,000 seconds. We were not patient enough to wait longer than 1,000 seconds to get the statistics that we needed, but that was a really good result and made it on the cover of Nature Physics. So we finally got a cover on something. The first experiment we did with trapped antihydrogen wasn't with lasers, but with microwaves. So you see, we added a microwave horn to a movable device that could shine microwaves down the axis. Now, why is that interesting? This is the Bright-Robbie diagram. It shows the energy levels of the hyperfine levels in the ground state of antihydrogen. These two states labeled C and D are the ones that are trappable because their energy increases as a function of magnetic field. So they're attracted to the center of the magnetic minimum trap. Using resonant microwaves, you can drive transitions from these trapped states to untrapped states, right? So if you're actually on resonance, you knock them out of the trap. Remember, that's what I said. Everything we do depends on that detection sensitivity. And this was the first time we were able to show that, again, published in Nature. First measurement, actual measurement on an antimatter atom. And you get a fundamental constant out of this. This is the magnetic moment of the antihydrogen atom. Right? So it's not just the Coulomb interaction that's tested by this physics, right? There's also fundamental constants like the magnetic moment of the atom. And this was important to us because it showed that we could do physics with a few atoms. After we did that, we decided, okay, Alpha, the original machine, wasn't designed to accept lasers. And so there was a shutdown coming in 2013. So in 2012, we removed the old machine and put in what we call Alpha 2, which had a little bit of separated function. The antiprotons were caught over here, then shuttled into another trap, which has the antihydrogen trap and also access ports for lasers. This has 8 superconducting coils inside, and all the experiments that we've done to date are in this machine. Here you can see it. The catching trap is on the left, the atom trap, laser access through the box here. So you get an idea of the scale of this. First experiment that we did in Alpha 2, this was just alluded to, is antihydrogen neutral? That's an experimental question, okay? We did a kind of a quick and dirty experiment through what we call stochastic acceleration. Trap some antihydrogen and then beat on it with random electric fields. If it has a charge, it'll eventually come out, okay? We did this experiment pretty quickly. All we know so far about the neutrality of this atom is that it's neutral to 0.7 parts per billion, whereas normal matter we know it's even better now, 1 part in 10 to the 21st, okay? Again, I will maintain this is an experimental question. You cannot assume this. All right. For the spectroscopy, this transition, the 1s to 2s, is in the ultraviolet. You need 2 photons at 243 nanometers. And to get enough light to actually excite this, you can't just shine a laser across the beam. You actually have to put the experiment in what's called a buildup cavity. So what happens here is that the laser enters from the left. Part of it goes through a mirror at this end. It gets bounced back, and you allow for coherent superposition of the wave bouncing back and forth by maintaining the length of this cavity to be an even number of wavelengths, right? So this is a common thing on your laser table in your laboratory. Putting it into 4 Kelvin ultra high vacuum was quite a challenge and was the main technical difficulty with this. the laser stuff, thanks to Professor Hangst and his developments and his offshoot companies, you can buy most of the equipment that you need to make the laser, and we just did that. So you can reference your laser. The initial frequency standard for alpha was a GPS disciplined clock using the frequency comb. That's the Nobel Prize winning technology for Professor Hangst. So this is all well established for hydrogen. We had to build this cavity using these mirrors to make it work for antihydrogen. Here are the energy levels, the 1s state on the bottom and the 2s state. So you're driving again between these two states. There are two transitions we call D to D and C to C. And again, the basic measurement is on or off. We put the laser on resonance and then see how many atoms are remaining after we've exposed it for a while. So here, the on resonance for a certain number of trials, we had 67, and off resonance 159, no laser 142. So it's just a 2-point spectroscopic measurement where we've shown that there's a resonance near where it's supposed to be with hydrogen, all right? So that was our first real breakthrough. I would say that we could actually see this transition that we've been trying to look at for so long. This was published in 2016. And as soon as you show up with a laser, you're testing CPT at 2 parts in 10 to the minus 10, right? And by this time we had about 15 atoms trapped at a time. Now, a little bit of history. The first time we trapped antihydrogen, we got this referee comment back in 2010. The very fact of a proof of principle demonstration of wall-free confinement of even a small number of antimatter atoms has an intrinsic philosophical value. Okay, I don't really know what that means, but I always challenge people when I give this talk, send me a better referee comment, right? Because you just typically don't get complimented by referees, right? Well, with the 1s, 2s, we finally got a better one. There's no doubt that this result is of high originality and of highest relevance to a broad scientific community, and thus merits publication in any journal the authors have selected. I congratulate the editors that the Alpha collaboration has selected Nature to publish this groundbreaking work. So that made my day. The Nature editors weren't amused, I think, but again, I'll throw down the gauntlet. If anyone can send me a better referee comment, I'll show it in all of my talks for the rest of my life. Okay, we've improved this microwave experiment. We could, knocking them out. And now, in fact, we can trap so many atoms and detect them so well that we can scan these two transitions in essentially real time. So what we're doing is, this is the microwave frequency on the x-axis and the number of counts that come out. And you see, you scan right over the first one, the C to B. And then there's a break here, which, by the way, is the 121 centimeter line in antihydrogen, right? This is the ground state hyperfine splitting that you're looking at here. And then you see the second line, right? This can be, you can sit in the control room now and watch this happen. It's almost, for us, it's completely over the top that we're allowed to do this. And there you get another fundamental constant, not with very high precision, but the ground state hyperfine splitting of antihydrogen. So if any alien radio astronomers out there, they can see this. Okay. We've also made progress on the spectroscopy. This is showing that first result, the 2-point, on-off measurement of the 1s, 2s line. In 2017, we've learned to do this a whole lot better. And you can see we're actually getting a line shape. And this is the source of the best CPT measurement in antimatter today. This is a relative precision about 2 times 10 to the minus 12. Remember, hydrogen, real hydrogen, they measure it at 10 to the minus 15. So we're getting better, but we still have a way to go. Right? Another Nature letter, and when Ted Hangst, who's the sort of godfather of hydrogen, gives a talk now, he shows this plot, which was the Hangst plot, but now with 2 points from antihydrogen. So we've actually made the big time if this guy is paying attention. Other lines, Lyman alpha, the 1s to 2p. This is, again, a fundamentally important transition, ubiquitous in astronomy. The so-called Lyman alpha forest is used for all sorts of techniques and calibrations in modern astronomy. We managed to do that with a pulse laser. I won't go into the details, but the difference here is now you're seeing the fine structure of, and you're looking at levels that have angular momentum, right? Obviously the S states have zero angular momentum. This so far is all in agreement. This transition will never give you the precision of the other one. It's a much faster, much broader line, but we've seen various lines within this manifold. Again, so far consistent with hydrogen. But there's another use for that laser, and that's the laser cooling transition. By the way, you can extract the Lamb shift from this last measurement that we made, published in 2020. By looking at the fine structure and the 1s, 2s, you can extract the Lamb shift. So to what degree is this all electrodynamic? Well, it all is, but it's not just the Coulomb interaction that you test with this. I mean, this is, the fundamental thing that inspired quantum electrodynamics, the Lamb shift. So again, it's electrodynamic, but it's not just Coulomb interaction. It's about vacuum fluctuations and so on. All of this physics must be the same for antihydrogen, right? Or there's something wrong with the standard model. Just to give you an idea of the state of the art now, we can accumulate antihydrogen atoms. In one of those mixing cycles, which takes 5 minutes now, we get about 20 atoms. But if we save them up for sort of 6 hours, we can get 1,000. And this is the first time we made more than 1,000, was in 2017. This is showing the number of annihilation vertices when we empty the trap. We're ramping down the magnets from 0 to 15 seconds here. So you're seeing the antihydrogen come out. And that's, anybody who started in this field when I did would think that this is just science fiction, that we would never ever have 1,000 trapped at once. Okay. Laser cooling, you've probably all heard about it. We'll just review it briefly. You're using the momentum of the photon to selectively decelerate particles. So a two-state atom absorbs a photon, it gets a recoil from the photon momentum. When it decays, you get sort of a dipole pattern of these photon emissions. For many of these events, this part averages, the recoil from this part averages to 0, and you can give a net momentum kick in the direction of the laser beam. Now, by detuning the laser beam to be below the resonance frequency, you only act on the particles that are moving towards the laser beam. Okay, so you have a velocity-dependent force, which is what you need for damping, right? This is not new. This has been around for 40 years or so. Revolutionized atomic physics that you can do this. Today, people get micro Kelvin temperatures by doing this with matter, and you can do this. You can buy a laser to do this, and it's very, very straightforward for matter. And for non-hydrogenic matter. Hydrogen, if forgive my language, is a bitch when it comes to laser cooling, right? And the reason is that this transition, the 1s to 2p, is at 121 nanometers. That's in the vacuum ultraviolet. You cannot buy a laser that makes that. You have to make it yourself. And this radiation doesn't travel through air. It has to, and there's only 2 materials that'll transmit it with any kind of degree of success at all. So it's really, really difficult to make and to work with, right? So in alpha, we do the same thing. We trap some antihydrogen. This, I won't go into the techniques. This laser was built by our colleagues in the University of British Columbia in Canada. It's a pulsed 10 hertz Lyman alpha laser. And there's the cooling transition. It's a particular transition that doesn't decay to a state that would be lost, because some of these decays involve a spin flip of the positron, which would mean you lose the atom. And the key thing here, if you know anything about laser cooling in matter, You have time constants typically of, milliseconds or even faster, because the atomic transitions can have nanosecond lifetimes. You can scatter enormous numbers of photons. In antihydrogen, because we have first so few atoms and so little light, we cool for hours, right, in order to see an effect. Now, the evidence for laser cooling is threefold, actually. The first thing is that if we measure the Lyman alpha line shape after laser cooling, that's the blue and the light blue here, it's narrower than with no cooling, or the red curve here is when we've intentionally heated the distribution by tuning the laser blue. Okay, so you can actually heat atoms with lasers also if you give them the wrong frequency. So this Doppler contribution to this line shape isn't dominant, but you can still see it here. The natural line width is larger than the Doppler width. So we're seeing an effect here. The difference here between cooling and stack and cool, cooling means we accumulate some antihydrogen and then apply the cooling laser. Stack and cool means we're applying the cooling laser while we're accumulating the antihydrogen. So we quickly realized that that was a better thing to do. Those 6 hours that we take for accumulating them can also be used in cooling. Now, the other thing that you see is what we call the time of flight spectrum. After the cooling, we can pulse this laser, excite another one of the Lyman alpha transitions that will flip the positron spin. So intentionally knock them out by choosing the line that has a branching ratio to one of the untrappable states. Now, what does that give you? You have a pulse laser and you have a detection of the particle, which is very fast. You can measure the time between those two, from the time you have the pulse until the time the antiproton hits the wall and annihilates. That gives you time of flight from the trap to the wall and gives you a direct measure of the transverse energy of the trapped particles. So you see when you do the cooling, the blue ones, you get lots more particles coming out later, right? So that's just number of events as a function of time. You have more cold ones that are taking longer to get out. The third evidence for laser cooling was actually going and measuring that very small line width in the 1s 2s transition. This is by far the most difficult experiment we've ever done, because it involves accumulating antihydrogen, cooling it for many hours, and then in the single fill, measuring this line shape. The last graph like this I showed you took 10 weeks to measure from 2017. In 2018, we can now do this experiment in 1 day. That was the last time we had beam. What you see here is that the width of this line gets about a factor of 4 narrower when you do the laser cooling. Now, this isn't a longitudinal Doppler effect. This is the so-called transit time broadening, because this transition is first order Doppler free, but there's a Fourier effect. The longer the atoms spend in the laser beam, the narrower the line can be. Right? So there's a transit time broadening, as it's known. If you're passing in and out of the laser beam, there's a delta F associated with that delta T. Cooling the atoms down makes that smaller. So this was just published on the 31st of March, just a week and a half ago. And we finally got on the cover of Nature after 19 years of trying, right? Now, this is really important for us. Everything that you do with antihydrogen, you'd like it to be colder. Both the spectroscopy to minimize all these contributions to the line width, so you can make a better determination of the line center, and also for gravity, obviously. If you're going to drop some antihydrogen, it's better if it's not flying all over the place while you drop it, right? So making it cold is, by the way, we've done a proof of principle experiment of how to measure gravity by releasing antihydrogen. We did this in the original alpha with a horizontal trap, just to show how you would do it, right? But now we're going to, and we have built a vertical machine we call alpha G, which has antihydrogen traps in it. The idea is very simple. You trap a lot of antihydrogen, you release it, You see the annihilations, see where it goes. Now, if it has a finite temperature, some of them are going to go up a little bit before they get lost. But statistically, you'll see the difference between down and up. We refer to this first measurement as the up-down experiment. Very few people believe that antihydrogen will fall up, but that number is not zero. There are lots of papers out there predicting repulsive gravity. We hope to be the first experiment to put this to bed. And we had hoped to do it in 2018, but didn't quite get there before CERN shut us down. Show you some, if you like hardware, we're not using silicon, we're using a time projection chamber. It's 3 meters long, roughly, the alpha G apparatus. The beam line, there's the external solenoid. On the right side, you see that there are 17 superconducting magnets in this cryostat. We built all this. So in May of 2018, our zone looked like this. What you're seeing on the left here is the alpha 2 atom trap. So normally this is the positron accumulator. It would have been mated here. We moved it downstream about 4 meters in May of 2018 and then inserted alpha G. So there you're seeing alpha G. It's about 3 stories high from the base of our. And between May and November of 2018, we actually installed all of this and got particles in it. The reason we were in such a hurry was because CERN was headed into what's called long shutdown 2, which started in November of 2018 and is still going on. So we were hoping to do a measurement before that happened, but we didn't quite make it. But you can see it's still, this is the group, a phenomenal effort by these people to get that all installed in less than 6 months. And we actually got particles, we trapped particles, we saw annihilations of antiprotons in the detector. By the way, here's a kind of proof of principle. These are antiprotons that we're knocking out, but we put some in this electrode so we can see how the detector works in the up position, put some in this electrode and let them release them. You can see the resolution. We can clearly see the difference between particles that go in either direction. Again, these are charged particles. With neutrals, it would look quite the same because we're only detecting the antiproton. Okay, so that's kind of where we stand right now. We're waiting until August of this year when we'll get some beam again. The other new aspect of this at CERN is they built us a new facility, which is called ELENA. That stands for Extra Low Energy Antiproton Ring. That'll take us from the 5 MeV of the AD down to 100 keV. And 2 things happen then. We can trap more, but because of the construction of this ring and the new beam lines associated with it, we think we can switch between experiments every shot. That means that all experiments could run for 24 hours a day rather than taking 8-hour shifts. And to us, this is not like a CERN experiment where you're sitting and collecting data for months and months to get some number of inverse nanobarns, right? We're always developing, always trying new techniques, and it's access to the antiprotons that limits progress. The experiments, when they happen in a week after 6 months of optimizing, right? So this is, we think, a real paradigm change for us. If we're able to work 24 hours a day, we can make progress much faster. So our first priority in 2021, when we get some beam back, is antimatter gravity. We want to, we've done a lot of spectroscopy so far, and we want to be the first to do this. The next step is then we want to try to compete with the hydrogen guys in antimatter spectroscopy. We want to get to that 10 to the minus 15 level. It's also possible to consider doing hydrogen measurements with some techniques. This trapped hydrogen laser cooled could also be a thing for matter physics. The long-term psycho possibility, anti-deuterium. Someone always asks this question, when are you going to do anti-helium? The answer to that is never. The wildest thing you could imagine would be anti-deuterium. I think you'd have to have a pretty good reason to go here. Like you've already seen some curious stuff in anti-hydrogen. This is not impossible. It might just be crazy enough to try. The best reason to get into antimatter physics is because all of my friends are rock stars. Here's David Crosby and Graham Nash, who dropped by one day. Muse, you may know Muse. Metallica, you know, the drummer from Metallica is a Dane. So I was surreal experience of discussing antimatter in Danish with Metallica. And we have this on the right. I printed this up. I was hoping they would sign it. It's Nothing Else Antimatters. If you're a Metallica fan, you'll get that. They both liked it and they posted it on their Instagram account. We get a lot of visitors coming through CERN. In 2018, 14,000 students, corporations, everybody comes. They like to see the AD. Jack White, Slayer, if you're into metal. I won't show you my pal Roger Waters because I know he's not popular in Israel. Okay, Alpha plus Carlsberg. I get a lot of money from the Carlsberg Foundation. If you've ever been in Denmark, you'll know what a civilized country it is, where the beer companies pay for fundamental research. Probably the best anti-hydrogen experiment in the world. I'm allowed to use that slogan. I have permission from the chairman, who is a physicist. Thank you very much for your invitation and for your attention. I'll be happy to answer your questions.
Yeah, thank you very much for this wonderful talk.
Thank you.
Maybe maybe first Helena, you have a question?
Hi, Helena.
Hi, Jeff.
How are you?
Congratulations.
Thank you.
Very good, yeah.
By the way, we should have full disclosure here. Helena used to be one of the referees for Alpha in the days before it worked. So she used to give me a really hard time.
Well, it worked, no?
It did, yeah, finally.
Well, actually, I wanted to ask you, what's happening with the other experiments, like ATRAP? You mentioned Aegis and G-bar for the
Yes.
gravity, and also ASAXA.
Yes.
Just few words, because I'm not completely up to date anymore.
Yeah, sure. So ATRAP no longer exists. They officially gave up, and their zone has been dismantled. I think that they just weren't making progress and couldn't get funding anymore. Aegis is proceeding. They're trying to do the anti-gravity measurement using this vertical interferometer, or the horizontal interferometer. G-bar has been built up over the last few years, and they actually took some antiprotons from ELENA in 2018. That's a very challenging experiment. They're very different techniques than what we're using. Just to say it briefly, in case people understand, they want to make the anti-hydrogen positive ion, that's an antiproton and 2 positrons, that's equivalent to H- in the matter world, then sympathetically laser cool that, and then photoionize it to drop it, to see how it behaves. So there's a whole lot of development they need to do. We're hoping that we get to the goal before them, because our experiment doesn't require any new development. We'll just turn Alpha on its head and do what we always do. ASAXA is working on antiprotonic helium still, this composite thing that's a helium atom with a captured antiproton as an orbital system. And also they've been trying to do a hyperfine measurement with antihydrogen, but haven't succeeded in making any measurement yet. There's also BASE. I don't know if BASE was there when they deal with precision measurements of the charge and the magnetic moment of the antiproton. That's a really impressive experiment. They're only dealing with antiprotons, not antihydrogen. But at one point, the magnetic moment of the antiproton was known with more precision than that of the proton. So those guys are really good and have a lot of nice results. So yeah, it's a really active program still, but ATRAP is gone.
I see.
Yeah, we have a question from Kobe.
Yeah, I would like to know whether you can trap, instead of positrons, mu plus to this antiproton. Well, I understand that there is such a thing with ordinary muons and protons.
Yes.
And the reason that I'm asking is that it might be a useful and very different way to determine the G-2 of the muon.
Yeah, I can promise you that I've been thinking about this. I'm just, I've been accused of being crazy for a long time, when I got into this. Now, this may be another level of crazy, but I think someone should do it. We don't have a good source of muons anywhere near right now, although obviously CERN could do that. but this would mean a major new facility to get yourself some muons. I have the same exact reaction. I would like to see that done, but there are lots of open questions in this type of physics these days, and mixing antimatter into it can only be good for everybody. But no, I don't have any plan to do that, and I'm not sure where you could do that. CERN is unique. You need CERN for the antiprotons, so we would have to get a muon beam from CERN. Now, having said that, you make the antiprotons by running protons into a target. You're producing a lot of pions in that target, and in principle, you could get yourself some muons. So I have enough to do, I guess, but that's not impossible. Let's put it that way.
Okay, thank you.
Good question.
Well, Jeff, if I can just add to it, the muon collider is not completely dead. In fact, it has acquired some momentum right now, and adding more physics to it could actually help all sides, right? The high energy and the low energy part.
What we can say now is that the anti-hydrogen part of it is routine now, right? And that's only now true. And I would say as of 2018, the last time we had beam, we can do this every day, right? And we can do spectroscopy every day. So yeah, it's definitely worth thinking about these things.
Maybe I can come back to Moti Mingum's question about, did you have a response from the theoretical community? I mean, are there already theories that your data can rule out, or are they interested at all?
Okay, here's where this fits in sort of modern theory world, as far as I understand. There's something called the standard model extension, which isn't so much a theory as it is a framework for imagining if there are terms, CPT violating terms or Lorentz violating terms in the Lagrangian, how would they show up in certain experiments, right? Now this is, the leader of this whole effort is a guy called Alan Kostelecki in Indiana, but there are a lot of people who have written about things like this. And they're the people who pay the closest attention to what we're doing. So this, again, this criticism about this only being electromagnetic, well, that's okay, but what if there are interactions we haven't thought about? And that's what the standard model extension is about. One is that I like to refer to it as the big red arrow. What if you have a local in Lorentz violation? Like there's a preferred direction in space. How does that show up in anti-hydrogen? All right, so that's the type of questions they ask. And you can always interpret our experiments as limiting some of the coefficients that they come up with in this Lagrangian. Now, as experimentalists, we've sort of made a decision not to speculate. Also because maybe, in 50 years, nobody will know about the standard model extension, but the experimental results will stand on their own. So we tend not to talk about this too much. Other experiments take a different approach and say, okay, we've eliminated this coefficient or limited to this much. So there's a framework for this. That's not the same as saying, somebody has a model of a new physics that would show up here.
May I add something, Yoni?
Sure.
Yeah. So another thing not to speculate about. There is this argument that if antimatter falls up, you can create a perpetual motion machine. You know about this argument?
Yes, I've heard about this.
So it's quite a simple argument. So basically what you are testing is conservation of energy. I mean, because if if antimatter can fall up, let's say you take a proton, you leave them in the gravitational field of the Earth, you don't lose energy because they just cancel, right? Because one is attracted, one is repelled. You let them annihilate, you get photons. Photons are just normal matter. You let them drop down, you gain energy, and then you let them create another pair, and so on and so forth. So it's a circle that creates energy. So we really expect, or are there really people in the world expecting, you said writing papers about antimatter falling up?
Yes, there's a few papers that claim that if there is repulsive gravity, that you can have a gravitational polarization of the vacuum, and that this would have profound effects on the evolution of the universe. So yeah, there are definitely papers about this. I don't really care. I'm going to measure it and get the truth, and then we can argue.
But you know, there may very well be particles that have negative gravitational mass. It's not the same thing as saying that antimatter has minus the mass of matter.
Are you saying that we
Just having some particles with negative masses doesn't create a perpetual motion machine. It is specifically antimatter, because you know that antimatter and matter can annihilate into normal matter.
But are you suggesting that we understand everything about gravity and we shouldn't do this measurement?
No. I'm not saying that you should not, but you know, one could measure whether two electrons or all the electrons have the same charge, things like this that we don't really know. You know, maybe they don't.
Yes.
But I don't think people write papers about it.
One thing I commonly meet is that people assume that quantum field theory is the end of where we're headed in studying physics. And I find that extremely arrogant.
That's not what I was saying. All I was saying is that you should know what you are testing. You're testing some principles that are extremely strong and are known to all. So it's not just, you know, CPT or things like this. You are really testing conservation of energy in one case. You know, you're testing charge conservation in another, things like this. It's important to know what is at stake.
I understand all that, and the stakes are very high. Obviously, my joke is that nobody believes in repulsive gravity, but I'll bet there are a lot of theorists who have a preprint under their mattress, so that when the experiment finds it, they can explain it.
Wouldn't it also mean that gravitational mass and the mass for acceleration are not the same if they're different for?
Yeah, that's what you're measuring. This experiment will technically measure the ratio of the gravitational mass to the inertial mass. That's the whole point.
Good. I think maybe let's thank Professor Hangst again, and if anybody has more questions, you can continue asking. I'll close down the recording. I have one more technical question to ask.
Okay.